Hello everyone and welcome to this deep dive into Universal Verification Methodology or UVM. Whether you are a seasoned verification engineer or just starting out, this video will cover everything you need to know about UVM, its component and how it revolutionizes the world of hardware verification. By the end of this video, you will have a solid understanding about UVM. So let's get started. Before we jump into UVM, let's quickly recap about what verification is all about. Verification is the process of ensuring that a hardware design like a microprocessor or a SoC behaves as intended. It involves creating test benches, writing test cases and stimulating design to catch the bug before the chip is manufactured. Without a proper verification, even a small bug can lead to a costly failure. So, what's UVM? UVM stands for Universal Verification Methodology. It's a standardized framework for building reusable and scalable test benches. UVM was developed by Estrella and is now the industry standard for system verification. Before UVM, verification engineers used methodologies like OVM and VMM. While they were effective, they lacked standardization, leading to inconsistencies across projects. UVM was introduced to provide a common framework for these methodologies. Now let's talk about the key features of UVM that make it so powerful. First, reusability. UVM promotes the creation of reusable components, reducing the time and effort needed for new projects. Then scalability. Whether you are verifying a small block or a full SoC, UVM scales to meet your needs. Then standardization. UVM provides a consistent structure, making it easier for teams to collaborate. Modularity. Test benches are broken into smaller, manageable components, improving maintainability. Randomization. UVM supports constrained random stimuli generation, which is crucial for uncovering corner case bugs. UVM's class hierarchy is built on system verilog's object-oriented features. The base class, UVM underscore object, handles data-related objects, while UVM underscore component structure the test bench where the elements like driver, monitors, and agents. Mastering these hierarchy is a key to efficient verification. Let's break down the architecture of a typical UVM test bench. It consists of several key components. First, test, the top level class that defines the test scenario. Then environment contain all the verification components like agents, scoreboards and checkers. Then agent manages the driver, monitor and sequencer for a specific interface. Then driver drives transaction to the DUT design under test. Then we go to monitor, observes the DUT's output and send it to the scoreboard. Sequencer generates and sequences transaction for the driver. Scoreboard compares the expected and actual results to verify correctness. Transaction flow through UVM test benches. Here is how data flows in a UVM test bench. The test creates a sequence of transactions which are sent to the sequencer. The sequencer passes these transactions to the driver which applies them to the DUT. The monitor observes the DUT's response and sends it to the scoreboard for comparison. If there is a mismatch, the test fails and the bug is flagged. Another important concept in UVM is phases. UVM test benches execute in a series of predefined phases such as build, connect, end of elaboration, start of simulation run, and report. These phases ensure that the test bench components are initialized and executed in the correct order. For example, the build phase constructs the test bench hierarchy while the run phase executes the test scenarios. One of the UVM's most powerful features is its support for constrained random stimuli generation. Instead of writing thousands of manual test cases, you can define constraints and let UVM generate random input that cover a wide range of scenarios. This approach is highly effective at finding corner case bugs that might be missed with direct testing. UVM reporting and debugging. Debugging is a critical part of verification and UVM makes it easier with built-in reporting mechanism. UVM provides macros like UVM underscore info, UVM underscore warning, and UVM underscore error to log messages during simulation. These messages help you to track down issues and understand what's happening in your test bench. Let's see UVM in action. Imagine you are verifying a simple FIFO. We create a UVM test bench with an agent for the FIFO's input and output interfaces. The driver pushes data into the FIFO while the monitor checks the output. The scoreboard ensures that the data comes out in the correct order. If everything matches, the data test passes. If not, we debug the issue using UVM's reporting tools. Advantages and challenges of UVM. So, why should you use UVM? Here are the top advantages: reusability, scalability, standardization, efficiency, and collaboration. Of course, UVM isn't without its challenges. It has a steep learning curve, especially if you are new to system Verilog or object-oriented programming. Additionally, setting up a UVM test bench can be time-consuming for small projects. However, the long-term benefits far outweigh these initial hurdles. Ready to dive into UVM? So let's get started. Learn system Verilog and object-oriented programming. Familiarize yourself with the UVM class library. Start with simple projects and gradually build more complex test benches. Use online resources, tutorials, and open source UVM examples. Practice, practice, and practice. And that's a wrap. We covered the basics of UVM. UVM is a game changer of hardware verification, and mastering it will take your skills to the next level. If you find this video helpful, then please like, share, and subscribe.